Supernovae don't go quietly, neither should your curiosity. Hit subscribe and explode into the cosmos with us. It begins in silence, not the quiet of an empty room, but the deeper hush of space, where sound has no air to ride and time stretches so thin it feels eternal. Out there, in the velvet dark between galaxies, a star is dying. Not with a whimper, not with a sigh, but with a gathering tension so immense it bends the rules of reality itself. You can't hear it. But if you could, if your ears could catch the tremors in space-time, you'd feel the heartbeat of a giant slowing, faltering, preparing for its final act. This star was never ordinary. Born in a storm of gas and dust, it gathered mass like a king claiming territory, 10, 15, even 20 times heavier than our sun. That weight was its glory and its doom. It burned brighter, hotter, faster. While our sun will live 10 billion years, this one raced through its life in just a few million. It fused hydrogen into helium, helium into carbon, carbon into oxygen, then neon, silicon, each stage shorter, fiercer, more desperate than the last. It was a cosmic forge, building heavier and heavier elements in its core, stoking its own funeral pyre. Now, in its final hours, something has changed. The light it casts, once steady, golden white flickers with unease. Deep inside, where pressures crush atoms like tin cans and temperatures soar past billions of degrees, the star has made a mistake. It has forged iron, and iron is poison to a star. Unlike every element before it, iron does not release energy when fused. It consumes it. The moment iron begins to pool in the core, the star's engine stalls. The fire that held back gravity for millions of years sputters out. Gravity, patient and relentless, has been waiting. For eons, it pulled inward while fusion pushed outward, a perfect, trembling balance. Now, with no pressure to resist it, gravity wins. In less than a second, the core collapses. Not slowly, not gently. It implodes at nearly 1/4 the speed of light. Electrons are crushed into protons. Neutrons are born in a flood. A sphere the size of Earth shrinks to the width of a city. And then something snaps. The collapse halts. Not because the star fights back, but because matter itself refuses to be squeezed further. Neutrons, packed tighter than atoms have ever been, push back with a force born of quantum law. The core stiffens like a bone. The infalling outer layers crash into this new, unimaginably dense surface and rebound. That rebound is the first whisper of the explosion. A shockwave, born in darkness, begins its journey outward through the star's own flesh. It will take hours to reach the surface. But when it does, when it finally breaks free into space, the star will not just die. It will scream its death across the cosmos in a flash so bright it outshines entire galaxies. For a few weeks, this single point of light will be visible in daylight, casting shadows at night, rewriting the map of the sky. And in that light, hidden in the fire, the ash, the expanding cloud of gas, will be the seeds of new worlds, of oceans, of life, of us. But right now, in this moment, there is only the quiet, the last breath before the storm, the universe holding its breath, waiting for the star to let go. To understand a supernova, you must first understand what a star truly is. Not just a pinprick of light in the night sky, not just a symbol in a poem, but a living engine of transformation, born from chaos, sustained by fire, and destined for an end written into its very birth. Stars begin as clouds. Vast, cold, and lonely, giant nurseries of hydrogen and helium, leftovers from the Big Bang, drifting through the void. But gravity never sleeps. Over millions of years, it tugs at these clouds, pulling clumps together. As the gas collapses, it heats up. Pressure builds. And when the core reaches about 10 million degrees, something miraculous happens. Atoms begin to fuse. Hydrogen nuclei slam together, overcoming their natural repulsion, and form helium. In that instant, a star is born, not with a cry, but with light. This fusion is more than just burning. It's alchemy. It's the universe learning to build. Every time two hydrogen atoms merge, a tiny bit of mass vanishes, and in its place, pure energy bursts forth, as Einstein's famous equation promised. That energy pushes outward, fighting the inward crush of gravity. For most of a star's life, this battle is in perfect balance. It's not static, it's dynamic, alive. The star breathes, pulses, sometimes swells, sometimes shrinks, but it holds. Our sun is a master of this balance. It fuses about 600 million tons of hydrogen every second. Yet it's so massive, it can keep this up for 10 billion years. But not all stars are like the sun. Some are born small and dim red dwarfs that burn so slowly they could outlive the current age of the universe. Others are born giants, blue-white titans, blazing with fury, consuming fuel at a catastrophic rate. These massive stars live fast. They shine brilliantly. And they die young. Why must they die? Because stars are not eternal. They are temporary solutions to a cosmic problem, how to turn simple elements into complex ones. Every fusion step releases energy, but only up to a point. Hydrogen to helium, energy released. Helium to carbon, yes. Carbon to oxygen, oxygen to silicon, still yes. But each step yields less energy than the one before. The star must burn hotter, denser, faster to keep the pressure up. It's like running uphill on a treadmill that keeps speeding up. And then comes iron. Iron is the ash of nuclear fire. It's the end of the line. Fusing iron doesn't give energy. It steals it. So when a massive star's core finally turns to iron, the engine stops. Not because it ran out of fuel, but because it made the wrong kind of ash. The star didn't fail. It succeeded too well. It built everything it could, right up to the element that kills it. This isn't tragedy, it's necessity. Without death, there is no renewal. Without supernovae, the universe would be stuck with only hydrogen, helium, and traces of lithium. No carbon for life, no oxygen to breathe, no iron in our blood. Stars must die so that something more complex can be born. So when we look up at the night sky, we're not just seeing lights, we're seeing ancestors. We're seeing furnaces that lived, burned, and gave everything they had. Not for glory, but for the chance that somewhere, someday, their ashes would gather into planets, oceans, and beings who could look back and wonder, where did we come from? The answer is, written in starlight and in death. Imagine building a house of cards. Each layer rests on the one below, held up by balance, tension, and just enough support. Now imagine that the final card you place doesn't strengthen the structure, it dissolves it. That's what iron does inside a massive star. It's not a villain. It's not a mistake. It's the natural end of a chain that began with the birth of the universe. But its arrival is the moment the house collapses. For millions of years, the star has been a layered onion of nuclear burning. At its heart, the hottest, densest region fuses silicon into iron. Surrounding that core are shells like rings in a tree, each burning a different fuel. Silicon outside the core, then oxygen, then carbon, then helium, and finally hydrogen at the very edge. Each shell feeds the one below, like a cosmic relay race passing energy inward. The star is a symphony of fusion, each movement shorter and more intense than the last. Silicon burning lasts only a day, oxygen a week, carbon a few hundred years. Helium maybe 1,000,000, but iron doesn't burn, it accumulates, and as it does, the core grows heavier, colder, deadlier. No new energy flows from it. The pressure that once held up the star's outer layers begins to fade. Gravity senses the weakness. It leans in. The core is now a sphere of iron and nickel, about the size of Earth, but weighing more than our Sun. Temperatures soar past 3 billion degrees. Yet instead of igniting, the iron nuclei begin to break apart. Photons, particles of light, become so energetic they start smashing iron atoms back into helium and neutrons in a process called photodisintegration. It's like the star's own light turning against it, tearing its core apart from within. This doesn't release energy. It consumes it, draining the last reserves of heat and pressure. At the same time, electrons, those tiny zipping particles that give atoms their structure, are being crushed into protons by the unbearable weight. They merge, forming neutrons and ghostly particles called neutrinos. This process, called electron capture, removes even more pressure. Electrons were part of what kept the core from collapsing. Now they're vanishing. The trap is sprung. Iron didn't explode the star. It simply stopped holding it up. And in the absence of support, gravity does what it always does. It pulls. Hard, fast, without mercy. In less than half a second, the core implodes. From a sphere the size of our planet, it shrinks to a ball just 20 kilometers across, denser than an atomic nucleus. A sugar cube-sized piece of this material would weigh as much as Mount Everest. Matter has been compressed beyond everyday comprehension. Atoms no longer exist. Only neutrons, packed shoulder to shoulder, exist in a state so extreme it defies laboratory replication. This isn't just collapse, it's transformation. The star's core is becoming something new, a neutron star, or perhaps, if it's massive enough, a black hole. But that's later. Right now, in this fraction of a second, the real drama is the violence of the rebound. As the core hits its quantum limit, when neutrons refuse to be squeezed any further, it stiffens like a spring coiled to its breaking point. The infalling outer layers, still racing inward at 70,000 kilometers per second, slam into this rigid surface and bounce back. A shockwave is born. It's weak at first, almost dying in the dense chaos. But deep in the core, trillions upon trillions of neutrinos, released in the neutron-forming frenzy, pour outward. They rarely interact with matter, but in this maelstrom, even a tiny fraction depositing energy is enough. They give the shock wave a second wind. This revived shock begins its journey through the star's layers. It will take hours to reach the surface, but when it does, the star will not fade quietly. It will explode with such violence that, for a brief time, it will outshine every star in its galaxy combined. And it all started with a single element. Iron, the ash that ended one life so that countless others could begin. There is a moment, so brief it defies human perception, when a star ceases to be a star. Not because it explodes, but because its heart vanishes into a state of matter so alien, so extreme, that it exists only in the most violent corners of the cosmos. This is the moment of collapse, not destruction, but metamorphosis. The star doesn't die all at once. Its core dies first. And in that death, it crosses a threshold into the unknown. Picture the core, A seething ball of iron, hotter than the center of any furnace, crushed under the weight of a star 10 times the mass of our sun. Gravity has won the war. Fusion has surrendered. Now, nothing stands between matter and oblivion. Electrons, once zipping freely, are forced into protons. Each collision births a neutron and a neutrino. The neutrinos flee, trillions of them, streaming out in a ghostly flood. The neutrons remain, packed tighter than marbles in a jar, then tighter still, until even the space between atomic nuclei disappears. The core becomes a single, city-sized atomic nucleus, a neutron star. But only if it's lucky. If the original star was heavy enough, say more than 20 times the mass of our Sun, the collapse doesn't stop at neutrons. Even neutron degeneracy pressure, that last quantum defense, fails. Gravity wins completely. The core keeps shrinking past the point of no return. Space itself bends inward. Time slows. Light cannot escape. A black hole is born, not with a bang, but with a silent, perfect erasure. This is the edge of nothing, not empty space, but a place where the rules of physics as we know them dissolve. We call it a singularity, though that word is more a confession of ignorance than a description. What happens inside, we don't know. General relativity says one thing. Quantum mechanics says another. They refuse to agree. And so, at the heart of a dying star lies a mystery the universe keeps to itself. But back in the outer layers, still falling inward at unimaginable speed, the story isn't over. These layers don't know the core is gone. They're still plunging toward a center that no longer exists in any familiar form. When they hit the newly formed neutron star or the event horizon of a black hole, they meet resistance. Or, in the black hole's case, they vanish without a trace. In the neutron star scenario, the impact is catastrophic. The infalling matter slams into the surface at nearly 1/4 the speed of light. The energy released is beyond comprehension, equivalent to detonating 100 octillion nuclear bombs at once. This collision sends a shockwave screaming back outward through the star's own body. It's like striking a bell the size of a solar system. The ring is a wave of pure violence. Yet even this shockwave is fragile. The star's outer layers are dense, chaotic, full of heavy elements and turbulent gas. The shock stalls. It loses energy. It threatens to fizzle out before it ever reaches the surface. For decades, astrophysicists puzzled over this. If the shock dies, how does the star explode? The answer came from the ghosts. Those neutrinos, the same ones produced when electrons and protons merged, are still flooding out of the newborn neutron star. In the first 10 seconds after collapse, 99% of the supernova's energy is carried away by these nearly massless particles. They pass through almost everything. But in the seething, opaque soup just outside the core, a small fraction, just 1%, interacts with the stalled shock. They deposit heat, they re-energize the wave. Like a whisper of breath reviving a dying ember, the neutrinos reignite the explosion. This mechanism, called neutrino-driven revival, is now the leading explanation for how most core collapse supernovae actually blow apart. It's not the bounce alone. It's the bounce plus the ghostly breath of a newborn neutron star. And so, from the edge of nothing, from the brink of total collapse, comes the spark of rebirth. The star, in its final act, uses the very particles that signaled its death to power its resurrection as a cosmic beacon. The collapse didn't end the story. It set the stage for the greatest light show in the universe. It begins deep inside, in darkness. A shockwave reborn by ghostly neutrinos starts its journey outward through the dying star. At first, it crawls, The star's interior is a labyrinth of dense gas, heavy elements, and turbulent currents. The shock fights its way through silicon, oxygen, carbon, helium, each layer like a wall of molten metal. It takes hours. But with every kilometer it travels, it gathers speed, heat, and fury. Then it hits the surface. The moment the shockwave breaches the star's outer envelope, the universe witnesses one of its most violent transformations. In a flash, literally, a point of light appears where none was before. Within minutes, it brightens exponentially. Within a day, it can outshine every star in its host galaxy combined. A single star for a few glorious weeks becomes brighter than 100 billion others burning together. This is not fire as we know it. There is no oxygen, no flame. This is pure radiative energy. Photons unleashed from nuclear chaos, racing outward at the speed of light. The explosion ejects the star's outer layers at speeds up to 10% the speed of light, 30,000 kilometers per second. That's fast enough to cross the distance from Earth to the Moon in just 10 seconds. The material doesn't just drift away. It blasts into space like shrapnel from a cosmic grenade, carving a bubble of hot gas that will expand for tens of thousands of years. What we see from Earth is the light curve, the rise and fall of brightness over time. It peaks not from the initial shock, but from the radioactive decay of newly forged elements, especially nickel-56. This unstable isotope, created in the furnace of the explosion, decays into cobalt-56, then into stable iron-56, releasing gamma rays with each step. Those gamma rays bounce around inside the expanding cloud, slowly turning into visible light. That's why a supernova doesn't fade immediately after the blast. It glows, powered by the slow death of atoms born in the explosion itself. The colors tell a story too. Early on, the light is blue-white hot, energetic, dominated by the shock-heated outer layers. As the cloud expands and cools, it reddens, spectroscopy. The splitting of light into its component colors reveals the chemical fingerprints of the ejector. Hydrogen lines? Then it's likely a Type 2 supernova from a star that still had its outer hydrogen envelope. No hydrogen, but helium. Type 1b, no hydrogen, no helium. Type 1c. Each signature is a clue to the star's final moments, its mass, its history. And the scale is humbling. In one explosion, a star can release more energy than our sun will emit in its entire 10 billion year life. The kinetic energy alone could power human civilization for millions of years if we could somehow capture it. But we can't. We can only watch and wonder. Historically, these events stunned ancient skywatchers. In the year 1054, Chinese astronomers recorded a guest star, so bright it was visible in broad daylight for 23 days. It cast shadows at night. They didn't know it was the death of a star 8,000 light-years away. They only knew the sky had changed. Today, we know that guest star became the Crab Nebula, a glowing cloud still expanding, with a pulsar at its heart spinning 30 times per second, the lighthouse of a dead star. That's the paradox of a supernova. It is destruction on a scale that erases worlds, yet it is also creation. The explosion doesn't just scatter debris, it seeds the galaxy with the ingredients for planets, for water, for life. Without this violence, the cosmos would be sterile, filled only with hydrogen and helium, forever simple, forever empty of complexity. So when you see a supernova in a time-lapse video, a sudden bloom of light in a distant galaxy, remember, you're not watching an end. You're watching a beginning. The moment a star gives everything it has so that something new can rise from its ashes. And somewhere in that expanding cloud, atoms are forming that will one day become part of a mountain, an ocean, or a living being who looks up and asks, "Where did I come from?" The answer is written in the light of that explosion. Not all stars die the same way. In fact, the universe has crafted two entirely different routes to supernova, one born of exhaustion, the other of betrayal. Both end in cataclysm. Both scatter stardust across the void. But their origins, their mechanisms, and even their cosmic roles are profoundly different. One is the death of a giant. The other is the murder of a thief. The first path, the one we followed so far, is core collapse. It belongs to massive stars, those born with at least 8 times the mass of our Sun. They live fast, burn through their nuclear fuel in layers, forge iron in their hearts, and collapse under their own weight. Their deaths are messy, asymmetric, often leaving behind a neutron star or black hole. They are the dramatic, chaotic finales of solitary titans. This is stellar death by natural causes, albeit on a scale that reshapes galaxies. But there's another kind of supernova, one that doesn't require a massive star at all. In fact, it often involves stars much smaller than our Sun. This is the Type 1a supernova, and it's not a collapse. It's a detonation. A thermonuclear bomb wrapped in starlight. And it begins not with a single star, but with two. Imagine a binary system, two stars orbiting each other, bound by gravity like cosmic dance partners. One is a white dwarf, a dead star, the Earth-sized ember of a sun-like star that long ago exhausted its fuel. It's dense, hot, and inert, made mostly of carbon and oxygen. The other is a living star, perhaps a red giant, swollen and unstable, spilling its outer layers into space. Over time, the white dwarf begins to steal gas from its companion. Hydrogen flows across the void, spiraling onto the white dwarf's surface. At first, this stolen fuel might ignite in small bursts, novae flashing brightly but leaving the star intact. But if the white dwarf keeps feeding, something dangerous happens. Its mass grows. White dwarfs are held up not by fusion, but by electron degeneracy pressure, a quantum rule that forbids electrons from occupying the same state. But this pressure has a limit. It's called the Chandrasekhar limit, about 1.4 times the mass of our Sun. Cross that line, and the star can no longer support itself. When the white dwarf tips over this edge, catastrophe follows in seconds. The core, now compressed beyond tolerance, heats to 600 million degrees. Carbon fusion ignites, not gently, but explosively. Unlike in massive stars, where fusion spreads in shells, here the entire star lights up at once. A thermonuclear flame rips through the white dwarf at 5% the speed of light. In under 20 seconds, the star is completely unmade. No core remains, no neutron star, no black hole. Just an expanding cloud of iron group elements. Nickel, cobalt, iron blasted into space at 10,000 kilometers per second. This is stellar suicide by overindulgence. The white dwarf didn't collapse. It detonated from within, consumed by the very fuel it stole. And because all Type 1a supernovae explode at nearly the same mass, the Chandrasekhar limit, they all shine with almost identical peak brightness. That uniformity makes them cosmic yardsticks. Astronomers use them to measure distances across the universe, leading to the shocking discovery that the universe's expansion is accelerating, a finding that earned a Nobel Prize. So while core collapse supernovae are diverse, chaotic, and tied to massive, star formation Type 1a supernovae are precise, clean, and act as universal beacons. One recycles heavy elements from massive stars. The other forges iron group elements in a flash of stolen gas. One leaves a corpse behind, the other vanishes without a trace. Yet both serve the same grand purpose. They enrich the cosmos. Without core collapse, there would be no oxygen, no silicon, no calcium. Without type 1a, there would be far less iron, the very element that carries oxygen in our blood. One builds the scaffolding of life, the other provides its metallic core. Two deaths, two mechanisms. One legacy, the transformation of simple gas into the complex chemistry of worlds. The universe doesn't care how a star dies, only that it dies well enough to give rise to something new. In the first second after a star's core collapses, something invisible steals the show. Not light, not heat, not even the shockwave. It's a flood of particles so elusive, so reluctant to interact with anything, that trillions of them pass through your body every second without a trace. We call them neutrinos. And in the heart of a supernova, they are the true architects of destruction and rebirth. When the iron core implodes, protons and electrons are crushed together under unimaginable pressure. They merge, forming neutrons, and in that instant, a neutrino is born. Not one, not 1,000, but about 10 to the 57th power, 10 billion trillion neutrinos, all released in a burst lasting just 10 seconds. This single event emits more energy in neutrinos than our sun will radiate in light over its entire 10 billion year life. And yet, if you were floating near the dying star, you wouldn't feel a thing. Neutrinos barely notice matter exists. They zip through planets, stars, even entire galaxies as if they weren't there. Their interaction with normal matter is so rare that a neutrino could pass through a light year of solid lead, about 9 trillion kilometers, and still have a 50-50 chance of making it through untouched. But inside the newborn neutron star, conditions are unlike anywhere else in the universe. The core is so dense, so hot, that even neutrinos, those cosmic ghosts, are briefly trapped. For a few crucial seconds, they scatter, bounce, and diffuse outward through the seething plasma. And in that brief window, something miraculous happens, a small fraction. Just 1% of these neutrinos deposit their energy into the stalled shockwave surrounding the core. This is the moment the supernova is truly born. Without this neutrino, reheating, the shockwave would fizzle out, swallowed by the infalling outer layers. The star might collapse silently into a black hole, leaving no explosion, no light, no legacy. But the neutrinos give it a second chance. They pour energy into the shock like a cosmic defibrillator, reviving it, pushing it outward with renewed violence. This mechanism, neutrino-driven explosion, is now the leading explanation for how most massive stars actually blow apart. We didn't always know this. For decades, simulations of core collapse kept failing. The shock would die. The star wouldn't explode. It wasn't until supercomputers could model the complex interplay of gravity, fluid dynamics, and neutrino physics in 3 dimensions that the picture came into focus. Even today, it remains one of the most computationally demanding problems in astrophysics. But we have proof, not just in code, but in real detection. On February 23, 1987, at 7:39 in the evening, a neutrino observatory buried deep in a mine in Japan recorded 11 neutrinos in a span of 13 seconds. Seconds later, another detector in Ohio saw 8 more. At the same time, in the southern hemisphere, astronomers noticed a new star blazing in the Large Magellanic Cloud, a small galaxy orbiting our own. It was Supernova 1987A, the closest observed supernova in nearly 4 centuries. The neutrinos arrived hours before the light. Why? Because they escaped the collapsing core immediately, while the shockwave took time to reach the surface. This was the first, and so far, only time we've directly detected neutrinos from a supernova beyond our solar system. It confirmed a theory decades in the making, that neutrinos carry the vast majority of a supernova's energy and play the decisive role in its explosion. Today, a global network of detectors, Super Kamiokande in Japan, IceCube in Antarctica, done under. Construction in the United States stands ready. They're not just waiting for the next nearby supernova. They're listening for the ghostly whisper of stellar death, hoping to catch the neutrino burst that heralds the birth of a neutron star or black hole. Because in that first second, before the light, before the sound, before the spectacle, lies the true heart of the supernova. Not in the fire we see, but in the invisible flood that makes the fire possible. The universe speaks in neutrinos, and in their silent rush, we hear the voice of creation itself. When a star explodes, it doesn't just scatter its remains, it creates new matter, not from nothing, but from the raw violence of the blast itself. In the heart of the supernova, temperatures and pressures soar beyond anything possible on Earth, turning the explosion into a cosmic forge where the heaviest, rarest, and most essential elements of life are born. This is not mere recycling. It's alchemy on a galactic scale. Most of the elements in your body, carbon, nitrogen, oxygen, were forged during a star's life in the gentle fusion of its core. But the periodic table doesn't end there. Beyond iron, the universe needed a more violent method. Iron is the dead end of fusion. To build heavier atoms, copper, zinc, iodine, gold, uranium, you need energy, not release it, and supernovae provide that energy in abundance. 2 key processes happen in the explosion. The first is called explosive nucleosynthesis. As the shockwave rips through the star's layers, it heats the gas to billions of degrees. In that inferno, atomic nuclei collide at tremendous speeds, fusing into new, heavier elements. Silicon fuses into iron group elements like nickel and cobalt. Oxygen and carbon form sulfur, argon, calcium. Much of the calcium in your bones, the potassium in your nerves, the sulfur in your proteins, these were cooked in the outer shells of a dying star during its final seconds. But the real magic happens deeper, in the seconds just after core collapse. Here, in the neutron-rich environment near the newborn neutron star, a different process takes over, the rapid neutron capture process, or R process. Free neutrons liberated during the collapse flood the surrounding material. Atomic nuclei, already heavy, begin to absorb these neutrons faster than they can radioactively decay. In under a second, a single seed nucleus can grow from iron to something as massive as uranium or plutonium. This is how the universe makes gold, platinum, europium, and other rare heavy elements. For decades, scientists debated where the R process occurred. Some thought neutron star collisions were the main source, but observations of old stars, those born shortly after the Big Bang, showed they already contained R process elements long before binary neutron stars could have merged. That pointed back to supernovae, especially rare, energetic types like hypernovae or magnetorotational explosions, as likely cradles of the heaviest atoms. Consider this: the gold in a wedding ring, the iodine in your thyroid, the zinc that helps your immune system, all were forged in the death throes of a star that lived and died before the sun was born. These elements were scattered across interstellar space, mixed into clouds of gas, and eventually folded into the next generation of stars and planets. Without supernovae, Earth would have no metals beyond iron, no electronics, no jewelry, no complex chemistry. Life as we know it would be impossible. Even the iron in your blood has a supernova origin. While some iron forms during a star's life, the vast majority, especially the stable iron 56 that dominates our planet's core and our hemoglobin, comes from the radioactive decay of nickel 56 created in the supernova explosion itself. The light curve of a supernova fades precisely because nickel turns to cobalt, then to iron, releasing energy as it goes. So, the very glow of the explosion is powered by the birth of the element that carries oxygen through your veins. This cosmic recycling is not random. It's precise, necessary, and ongoing. Every time a massive star dies, it enriches its galaxy with a new batch of elements. Over billions of years, this enrichment transforms galaxies from simple hydrogen clouds into chemically rich ecosystems capable of forming rocky planets and organic molecules. And it's not just about quantity, it's about distribution. The explosion doesn't just make elements, it flings them far and wide. Shockwaves compress nearby gas clouds, triggering the birth of new stars. Those newborn stars form with heavier elements already in their makeup, allowing planets like Earth to coalesce from metal-rich dust. So when you hold a piece of metal, breathe oxygen, or feel your heart pump iron-rich blood, you are touching the legacy of stellar death. The supernova didn't just happen out there, it happened in here, in the atoms that make you. Destruction was the price of complexity, and the universe paid it willingly, again and again, across billions of years, so that one day Stardust could wake up and wonder at itself. For most of human history, the night sky was a canvas of permanence. Stars were fixed, eternal, divine. Then, without warning, a new light would appear, brighter than any star, sometimes visible in daylight, only to fade weeks or months later, never to return. Ancient astronomers called them guest stars. They didn't know they were witnessing death, but they recorded it with awe and precision. The earliest known supernova sighting comes from Chinese skywatchers in the year 185. They described a broom star that stayed visible for 8 months. In 1054, another guest star appeared, so brilliant it cast shadows at night, and was seen in broad daylight for 23 days. Arab, Japanese, and possibly Native American observers noted it too. That explosion, 8,000 light-years away, left behind the Crab Nebula. A swirling cloud of gas we now know hides a pulsar spinning 30 times every second. But for centuries, these events were mysteries. Were they atmospheric? Divine omens? It wasn't until the invention of the telescope, and later, photography and spectroscopy, that humanity began to understand what these flashes truly were. In the 1800s, astronomers started systematically cataloging the sky. When a new star appeared in the constellation Cygnus in 1875, they could compare it to earlier star charts and confirm it hadn't been there before. The term nova, Latin for new, was born. But soon, they realized some of these new stars were far brighter than others. In 1938, astronomers Walter Baade and Fritz Zwicky made a crucial distinction. They proposed that the fainter novae were surface explosions on white dwarfs, while the truly brilliant ones, like the guest star of 1054, were the catastrophic deaths of entire stars. They called these supernovae. Zwicky, a brilliant and eccentric physicist at Caltech, went further. He suggested that supernovae marked the birth of neutron stars, objects so dense that a teaspoon would weigh billions of tons. At the time, it sounded like science fiction. Neutrons had only just been discovered. The idea that an entire star could collapse into one seemed absurd. But Zwicky was right. The real breakthrough came with light itself. By splitting starlight into spectra rainbow-like bands with dark or bright lines, astronomers could read the chemical composition of distant objects. In the 1940s, they noticed that some supernovae showed strong hydrogen lines, others showed none. This led to the classification we still use, type 2 with hydrogen and type 1 without. Later, type 1 was split again into 1A, 1B, and 1C based on other elements, revealing the two distinct origins we now understand. Then came the digital age. Automated telescopes now scan the entire sky every few nights, comparing new images to old ones, hunting for sudden points of light. Projects like the Zwicky Transient Facility, named in honor of that visionary, discover thousands of supernovae each year. What was once a rare celestial omen is now a routine cosmic event, studied in real time across the electromagnetic spectrum, from radio waves to gamma rays. But the most profound shift came not from light, but from particles. In 1987, when supernova 1987, A exploded in the Large Magellanic Cloud, neutrino detectors on Earth caught the ghostly burst from its core collapse, hours before the light arrived. It was the first direct confirmation that supernovae are powered by neutrinos, and that core collapse happens exactly as theory predicted. Today, we don't just observe supernovae, we use them. Type 1A supernovae, with their uniform brightness, became the key to measuring the expansion of the universe. In the late 1990s, two teams of astronomers used them to discover that cosmic expansion is accelerating, a revelation that implied the existence of dark energy and reshaped cosmology forever. From ancient scribes to neutrino observatories, humanity's journey to understand supernovae mirrors our larger quest to see the universe not as a static backdrop, but as a dynamic, evolving story, one written in light, in atoms, and in the echoes of stellar death. And every time we witness a new supernova, we're not just watching a star die. We're reading a page in the cosmic autobiography written long ago, but only now being understood. You are not separate from the cosmos. You are part of it, literally, atom by atom. And the most intimate connection you have to the universe isn't through wonder or philosophy, but through chemistry. The calcium in your bones, the iron in your blood, the oxygen you breathe, the zinc in your enzymes. All of it was forged in the hearts of stars that lived and died long before the sun was born. And the heaviest, rarest pieces of you, those came from supernovae. Think about your left hand. The carbon atoms in your skin were made in the quiet fusion of a star like our sun. But the iron in the hemoglobin carrying oxygen through your veins, that came from a supernova. The iodine regulating your thyroid, supernova. The copper helping your brain fire signals, supernova. Even the potassium that keeps your heart beating. Much of it was scattered by an exploding star. This isn't poetry, it's forensic astrophysics. We know because we can measure the composition of the sun, of meteorites, of ancient stars, and of human tissue, and they all tell the same story. The early universe contained only hydrogen, helium, and trace lithium. Everything else, every element on the periodic table beyond number 3 was built later in stars. And elements heavier than iron? They require the extreme conditions of a supernova or a neutron star collision. Without those violent deaths, the universe would be chemically simple, sterile, incapable of forming planets, water, or life. But it's not just about having the right ingredients, it's about mixing them. A supernova doesn't just create elements. It blasts them into space at thousands of kilometers per second, seeding vast clouds of gas with a rich chemical broth. Over millions of years, gravity pulls these enriched clouds together. New stars form, surrounded by disks of dust and gas that now contain carbon, oxygen, silicon, iron, and more. In those disks, dust grains stick together, grow, and eventually become planets. Earth is a product of that enrichment. Our planet's core is mostly iron delivered by countless supernovae over billions of years. Our crust is rich in oxygen, silicon, magnesium, all forged in massive stars. The oceans exist because oxygen combined with hydrogen, and that oxygen came from stars that died before the sun ignited. And then there's life itself. DNA, proteins, cell membranes, they all rely on elements that only supernovae could provide in sufficient quantities. Take phosphorus, essential for energy transfer in every living cell. It's made primarily in the oxygen-burning shells of massive stars and scattered by supernovae. Or selenium, a trace element vital for human health, produced almost exclusively in the R process during core collapse. Even your sense of self, the electrical impulses in your brain, depends on ions like sodium, potassium, and calcium. Those atoms were once part of a star's outer layers, torn apart in an explosion so violent it briefly outshone a galaxy. They drifted through the interstellar dark for millions of years, cold and inert, until they found themselves in a collapsing cloud that would become the solar system. They were baked into rocks, dissolved in oceans, absorbed by plants, eaten by animals, and finally assembled into you. This is the profound truth of supernovae. They are not distant spectacles. They are ancestral events. Every breath you take contains oxygen atoms that were once inside a star 10 times the mass of our sun. Every heartbeat pulses with iron forged in a core that collapsed in less than a second. You carry the ashes of dead stars in your cells, not as metaphor, but as measurable, undeniable fact. And because of that, you are also a witness. You are the universe's way of looking back at its own history. When you gaze up at the night sky and wonder about your place in it, you're not just a passive observer. You are stardust that has become conscious capable of remembering the explosions that made you possible. That's why supernovae matter. Not just to astronomers, but to everyone. They remind us that death is not an end in the cosmos. It's a necessary act of generosity. A star gives its life not for itself, but for what comes after. And in doing so, it makes beings like us possible, fragile, temporary, but capable of awe, of love, of understanding that we are made from the remains of giants who died so we could live. So the next time you feel small under the vast sky, remember, you are not insignificant. You are the universe reborn, and the fire that once lit a dying star now burns quietly in your chest. In the grand theater of the cosmos, supernovae do more than scatter stardust. They serve as lighthouses, timekeepers, and cosmic yardsticks. Among them, one type stands out not for its violence, but for its precision, the Type 1a supernova. These stellar explosions are so uniform in brightness that they become one of the most powerful tools in astronomy, allowing us to measure distances across billions of light years and uncover the deepest secrets of the universe, including its accelerating expansion. The key lies in their origin. As we've seen, Type 1a supernovae occur when a white dwarf in a binary system steals enough mass from its companion to reach the Chandrasekhar limit, about 1.4 times the mass of our Sun. Because this critical mass is nearly identical every time, the resulting explosion releases almost the same amount of energy. That means every Type 1a supernova reaches almost the same peak brightness. In astronomy, such objects are called standard candles, not because they're ordinary, but because their intrinsic luminosity is known. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance. It's the same principle that lets you judge how far away a car's headlights are on a dark road. The dimmer they look, the farther they are. By observing Type 1a supernovae in distant galaxies, astronomers can determine how far those galaxies lie from us with remarkable accuracy. In the late 1990s, two independent teams, the Supernova Cosmology Project and the High-Z Supernovae, search team used this method to map the expansion history of the universe. They expected to find that gravity was slowing cosmic expansion, as all models predicted. Instead, they found the opposite. The most distant supernovae were dimmer than expected, meaning they were farther away than predicted. The universe wasn't just expanding, it was accelerating. This discovery was revolutionary. It implied the existence of a mysterious force now called dark energy, a repulsive energy woven into the fabric of space itself, pushing galaxies apart at an ever-increasing rate. The finding was so unexpected, so profound, that it earned the two team leaders the Nobel Prize in Physics in 2011. But Type 1a supernovae aren't perfect. Astronomers have since learned that their peak brightness can vary slightly depending on the composition of the white dwarf or the nature of its companion star. To account for this, they use a clever trick. They observe how quickly the supernova's light fades after peak brightness. Brighter supernovae fade more slowly, dimmer ones fade faster. This light curve width luminosity relation allows them to fine-tune each measurement, turning Type 1a explosions into even more precise cosmic rulers. Meanwhile, core collapse supernovae, though far more diverse, also offer clues. Their rates tell us how fast stars are forming in distant galaxies, since only massive, short-lived stars produce them. By counting supernovae over cosmic time, we can trace the history of star birth across billions of years. And there's another layer: time delay. Because light takes time to travel, when we observe a supernova in a galaxy 1 billion light-years away, we're seeing an explosion that happened 1 billion years ago. By studying supernovae at different distances, we're effectively looking back in time, watching how the universe behaved in its youth, middle age, and recent past. This cosmic archaeology has revealed that star formation peaked about 10 billion years ago and has been declining since. It has shown how galaxies evolve from chaotic, gas-rich systems into the orderly spirals and ellipticals we see today. And it has confirmed, again and again, that the laws of physics are the same everywhere, from our backyard to the edge of the observable universe. So a supernova is not just an end, it's a signal, a beacon, a clock ticking in the dark. In its light, we read the story of space, time, and expansion. We measure the unseen dark energy, dark matter, the curvature of space-time, and we do it all using the death throes of stars that exploded long before Earth existed. That's the quiet miracle of the Type 1a supernova, a stellar suicide so consistent, so reliable, that it lets us weigh the universe itself. In the ashes of a dead star, we find the scale of all that is. Not every massive star ends with a bang. Some vanish without a trace. No flash, no expanding nebula, no cosmic fanfare. They simply wink out of existence, swallowed whole by their own gravity. These are the failed supernovae, the quiet deaths that challenge our understanding of stellar evolution and reveal the universe's most extreme outcome: direct collapse into a black hole. For decades, astronomers assumed that all stars above 8 solar masses would explode as supernovae. But observations began to tell a different story. In galaxies where massive stars are born, we see far fewer supernovae than expected. Some giants seem to disappear without a trace. The leading explanation: they collapse directly into black holes, bypassing the explosion entirely. How does this happen? It comes down to mass and momentum. In a typical core collapse supernova, the shockwave revived by neutrinos blasts the outer layers into space. But if the star is extremely massive, say over 25 times the mass of our Sun, the core may be so heavy that even the neutrino-driven shock can't overcome the inward pull of gravity. The shock stalls. No revival, no explosion. The entire star implodes, vanishing behind an event horizon before any light can escape. In some cases, the star might shed its outer layers through powerful stellar winds before death, leaving a bare helium core. If that core is massive enough, it too can collapse directly. No hydrogen, no helium shell to light up, just silence. The first strong candidate for a failed supernova appeared in 2017. Astronomers had been monitoring a red supergiant star in a galaxy 22 million light-years away. It was bright, stable, and unmistakable. Then, in 2009, it was gone. No supernova, no fading glow, just absence. Follow-up observations with the Hubble Space Telescope confirmed the star had vanished. The most plausible explanation: it collapsed straight into a black hole. This changes how we think about black hole formation. Not all black holes come from supernovae with messy explosions and neutron star intermediaries. Some are born in perfect silence, the ultimate cosmic vanishing act, and the implications ripple outward. Failed supernovae mean fewer heavy elements are scattered into space. That affects how galaxies enrich their gas over time. It also means the population of stellar mass black holes may be larger than we thought, many of them invisible, detectable only when they pull matter from a companion star or merge with another black hole, sending ripples through space-time as gravitational waves. In fact, the black hole mergers detected by LIGO and Virgo, like the famous event in 2015, likely came from stars that either experienced weak supernovae or none at all. If a supernova is too energetic, it can kick the newborn black hole out of its binary system, preventing future mergers. But a quiet collapse leaves the black hole in place, ready to dance with its partner for millions of years before colliding. So, the silence of a failed supernova isn't empty. It's full of consequence. It shapes the black hole population. It alters chemical evolution. It reminds us that the universe doesn't always announce its transformations with light. Sometimes, creation happens in darkness. And that raises the haunting question: how many black holes are out there, born in silence, drifting unseen through the galaxy? We may never know their number, only infer them from what's missing: the supernovae that never happened, the stars that simply ceased to be. In the end, even failure serves the cosmos. A star that dies quietly still contributes to the universe's structure. Not by scattering elements, but by adding to the invisible scaffolding of dark, dense objects that shape galaxies through gravity alone. Death in the universe has many forms. And sometimes the most powerful endings are the ones no one sees. It's not a matter of if, but when. Somewhere in our galaxy, a massive star is living its final days. It could be Betelgeuse, the red supergiant in Orion's shoulder, already swollen and unstable, just 640 light-years away. Or it could be Antares, or Spica, or an unnamed star hidden behind dust in the galactic plane. One of them will explode. And when it does, it will be the most spectacular astronomical event in human history. Unlike distant supernovae seen as faint points in faraway galaxies, a Milky Way supernova would be close enough to transform our night sky, ignite global wonder, and revolutionize astrophysics overnight. At its peak, it could shine as brightly as the full moon, visible even in broad daylight for weeks. At night, it would cast sharp shadows, illuminate clouds from below, and outshine every star in the sky combined. Ancient records tell us it's happened before. Most recently, in 1607, though obscured by dust, but never in the age of telescopes, satellites, and neutrino detectors. We are ready. A global network of observatories, optical, radio, X-ray, gamma ray, is already on standby. But the real early warning won't come from light. It will come from neutrinos. The moment a core collapses in our galaxy, detectors like Super Kamiokande in Japan, Ice Cube in Antarctica, and the upcoming Dune in the United States will light up with thousands of neutrino interactions within seconds. These ghostly particles will arrive hours before the first visible light, giving astronomers precious time to point every telescope on Earth and in space toward the source. This would be more than a show. It would be a scientific goldmine. For the first time, we could watch a supernova unfold in real time, from the neutrino burst through the shock breakout, the rise to peak brightness, and the slow fade powered by radioactive decay. We could test our models of explosion physics, probe the birth of a neutron star or black hole, and measure the R process in action. We might even detect gravitational waves from asymmetries in the collapse, ripples in space-time from a dying star in our own galactic neighborhood. And the public? They would witness something profound. In an age of screens and noise, a supernova would pull humanity's gaze upward, together. Schools would pause. Cities would dim lights to see it better. Philosophers, poets, and children would all look at the same point in the sky and feel the same awe. It would be a shared moment of cosmic perspective, reminding us that we live in a dynamic universe, where stars are born, live, and die, and where we are made of their remains. But what about danger? Could a nearby supernova harm Earth? The answer is reassuring for the most part. A supernova would need to be within about 50 light-years to pose a serious threat from gamma rays or cosmic rays. Fortunately, there are no stars massive enough to go supernova that close to us. Betelgeuse, at 640 light-years, is far enough that its explosion would be dazzling but harmless. The radiation would be diluted by distance, and our atmosphere would shield us. In fact, some scientists speculate that past supernovae, hundreds of light-years away, may have left traces in Earth's geology, like iron-60 isotopes in ocean crust, but without mass extinctions. Still, the psychological impact would be immense. For the first time, people would see stellar death not as an abstract concept, but as a visible, undeniable event. They'd understand, viscerally, that the universe is not static, that change, even violent change, is woven into its fabric. And when it fades, after weeks or months, the sky would return to normal. But we would not. we'd carry the memory of that light, knowing it came from a star that gave its life to enrich the galaxy. And somewhere in that expanding cloud, new stars would one day form, seeded with the elements forged in the blast. The next galactic supernova isn't just an astronomical event. It's a rendezvous with cosmic time. It's the universe knocking on our door, saying, "Remember where you came from." And when it happens, we'll be watching, not just with instruments, but with hearts wide open. The explosion ends, the light fades, but the story is far from over. Long after the supernova's brilliance dims into memory, its legacy lingers in expanding clouds of gas, in spinning stellar corpses, in the very chemistry of future worlds. What remains is not ruin, but raw material. Not silence, but the seed of new beginnings. The most visible remnant is the supernova remnant itself, a vast glowing shell of ejected material racing outward at thousands of kilometers per second. At first, it's a chaotic fireball heated to millions of degrees, emitting X-rays as it slams into the surrounding interstellar medium. Over centuries, it cools, fragments, and mixes with the galaxy's gas. Famous examples like the Crab Nebula or Cassiopeia A are not just beautiful, they're cosmic laboratories, revealing how shock waves accelerate particles to near light speed, creating cosmic rays that zip through space and even reach Earth. These remnants can span dozens of light years and glow for tens of thousands of years. Their filaments, glowing red from hydrogen, green from oxygen, blue from X-ray emitting gas, are the fingerprints of the star's final moments. By studying their structure, composition, and motion, astronomers can reconstruct the explosion's energy, asymmetry, and even the type of star that died. At the center of many remnants lies the collapsed core, the true survivor of the cataclysm. If the original star was between about 8 and 25 solar masses, what's left is a neutron star, a city-sized sphere of pure neutrons, spinning rapidly, often with a powerful magnetic field. Some, like the one in the Crab Nebula, beam pulses of radiation like cosmic lighthouses. Pulsars. Others, with magnetic fields a quadrillion times stronger than Earth's, are magnetars, capable of starquakes that release more energy in 1/10 of a second than the Sun does in 100,000 years. If the progenitor star was even more massive, the core collapsed beyond the neutron star stage, vanishing into a black hole. No light escapes it, but if it's in a binary system, it may pull gas from its companion, heating it to X-ray temperatures, a telltale sign of its presence. In isolation, it drifts invisibly, detectable only by its gravity. But the most profound legacy isn't visible at all. It's chemical. The supernova has seeded the galaxy with heavy elements: oxygen, silicon, sulfur, calcium, iron, gold, scattered across hundreds of light years. Over millions of years, this enriched gas cools, condenses, and becomes part of new molecular clouds. When those clouds collapse to form new stars and planets, they carry that stardust within them. Our solar system is a direct beneficiary. Meteorites, ancient rocks left over from planet formation, contain microscopic grains of silicon carbide and graphite that formed in the outflows of ancient supernovae. These pre-solar grains are older than the Sun itself. They carry isotopic signatures that match supernova models perfectly. They are literal stardust, preserved for 4.6 billion years. Even the structure of our galaxy bears the imprint of supernovae. Their shock waves compress gas clouds, triggering waves of star formation. They help regulate the temperature and density of the interstellar medium, preventing galaxies from collapsing too quickly into stars. In a real sense, supernovae act as cosmic thermostats, balancing creation and destruction on a galactic scale. And then there's time. A supernova remnant may fade from view in 100,000 years, but its atoms endure. The iron it forged will cycle through stars, planets, and perhaps life over and over. In 10 billion years, those same atoms might be part of another world, orbiting another star, in a galaxy transformed by countless such explosions. So when we look at a supernova remnant through a telescope, we're not seeing an end. We're seeing a middle chapter. The fire has cooled, but the story continues in every new star born from its ashes, in every planet that forms from its dust, in every living thing that breathes its oxygen. The universe doesn't waste death. It recycles it, and in that recycling, it builds complexity, beauty, and consciousness. The legacy of a supernova isn't just light or gas or a spinning neutron star, it's the possibility of something new, something like us. There is a moment late at night when the sky is clear and the world is quiet, that you can feel it, the deep, quiet hum of connection between you and the stars. It's not mystical, it's molecular. Every atom in your body that is heavier than hydrogen and helium was forged in the heart of a star, and the heaviest among them. The iron in your blood, the iodine in your mind, the gold that might rest on your finger were scattered across the galaxy in the violent death of a supernova. You are not just in the universe. You are the universe, awake, aware, and looking back at itself. This is not a metaphor. It is a fact written in the language of physics, confirmed by spectroscopy, meteorites, and neutrino detectors. The calcium that strengthens your bones was cooked in the oxygen-burning shell of a massive star. The oxygen you breathe was fused in the core of a red giant. The carbon in your DNA was forged in the gentle fires of a sun-like star. But the rare, dense, essential metals that make complex life possible, those came from the R process in the first seconds of a supernova explosion, or perhaps in the collision of neutron stars born from such explosions. And because of that, you carry within you the memory of stellar death, not as sorrow, but as gift. A star lived for millions of years, burning fuel, building elements, holding itself together against gravity's pull. Then, in its final act, it gave everything, not for itself, but for what would come after. It exploded, scattering its enriched guts across light years of space, so that one day, in a quiet corner of a spiral arm, a cloud of gas and dust could collapse into a new star, a new planetary system, and eventually, beings who could ask, "Why are we here?" The answer is written in your cells. Supernovae are not just astronomical events. They are the universe's way of evolving from simplicity to complexity. Without them, the cosmos would be a sea of hydrogen and helium, eternally simple, eternally empty of planets, oceans, or life. They are the necessary violence that makes tenderness possible, the fire that forges the tools of creation. And now, after billions of years of the cycle star birth, star death, enrichment, rebirth, we have arrived. Conscious Stardust, beings who can look up at the night sky and recognize their ancestors in the light of distant stars, who can build telescopes to catch the ghostly neutrinos from a dying star, who can decode the spectra of supernova remnants and read the chemical story of their own origin. That is the miracle. Not that stars explode, but that from those explosions, something like us could emerge. Fragile, temporary, yet capable of awe, of love, of understanding that we are made from the remains of giants. So the next time you feel small beneath the vastness of the cosmos, remember, you are not insignificant. You are the universe experiencing itself. You are the calcium from a red supergiant, the iron from a core collapse explosion, the oxygen from a long-dead star, all assembled into a being who can wonder, create, and care. And in that wonder, the universe finds its voice. The story of Supernovae is not just about death. It's about generosity, about transformation, about the relentless drive of matter to become more than it was. A star dies so that a planet can form. A planet forms so that life can arise. Life arises so that consciousness can emerge. And consciousness emerges so that the universe can finally see itself, not as a collection of particles, but as a story worth telling. We are that story. And every time we look up at the stars, not with fear, but with gratitude, we honor the explosions that made us possible. So let the night sky remind you, you belong here, you are home. And the fire that once lit a dying star now burns quietly in your chest, in your mind, in your hands, ready to create, to connect, to continue the story. Because the universe didn't just make you, it made you to remember.